Good morning, hello. Physics C, Electromagnetism, AP course, class number 2. Today we're talking about electric fields. So we already talked about in Coulomb's law. Whoop, ooh, blue. There we go. So we established that force, electromagnetic field, equals K Q1 Q2 over R squared. And that's what gave us the force between two charged particles. We have a plus over here, negative over here, and the force experienced between the two would be towards each other, one on the other on the one, of F equals K, this is a K, Q over R squared. And there's this in the radial direction, and then that force is a vector, meaning it has both magnitude and direction. Purple. So what electric field does for us is it takes this portion right here and it says that is the electric field. So force then we will then write as electric field times Q, where electric field is a vector field. So what's nice about this is, now your thoughts is, well, why don't we just stick with the Coulomb's law? First place, seems like we're making things unnecessarily complicated here. Let's just keep everything as obvious and out there as possible, which is a good point. What this allows us to do is basically ignore the first charge and then bring another charge in. So if we have like an electric field, let's grab a positive electric field. Here we go. Positive electric field. And maybe I'll leave that one there. Let's grab a copy. Copy paste. So if we have an electric field, this will be positive. And we have a charge, we'll call him negative over here. The idea is we can have this electric field, and then all we have to worry about with our calculations then is bringing in one charge. The value of this is then we can make complex arrangements. So far we've only dealt with point charges for Coulomb's law, and we have superimposed them with other point charges. And the idea then is we can superimpose multiple, a plethora of charges, point charges, and so then it's easier for us to look at the electric field at any given time and do vector to vector, and then we can say, all right, so the electric field in this case at that point is a sum of those. That's the value added by having electric fields. So to go over some conventions of electric fields, we have electric fields for positive and negative. Nope, I wanted this one. Copy, paste. There we go. So looking at Coulomb's law, for a point charge, we know that the force is radially symmetrical, same in all directions. Here it's 2D, in reality it's 3D. And by convention, the electric field lines, which go in the same, when drawn, the electric field lines go in the same direction as the electric field, go out from the positive and in to negatives. So this would be a positive, this would be a negative. So at this point here, the electric field, which we then would use as the formula for electric field, E times Q, to convert it to a force. So if we place a charge here, we'll say a positive charge, that way it's repelling, it would be forced in that direction. And you can see how the electric field lines kind of expand outwards. Another convention with electric field lines is that, for starters, they never cross. And the density in a given area of electric field lines would then give you the magnitude of the electric field at that point. So here, for a given area of about the same size, we have 3 lines that are crossed. Here we only have 1. So the magnitude here would be larger than the magnitude here. I try not to get too specific on how much larger, because this is just pictures and I'm a terrible artist. So I put minimal faith in my artistic skills. So you've also seen that, you've probably seen a picture of a dipole with electric fields. So you have something like a positive charge over here, negative charge over here, and let's move these closer. And you've seen something like purple. No, yeah, I'm good with that. Something kind of like this. We see electric field lines going from, and then it kind of curves over lazily. This will also lazily curve over, and this kind of, with an excessively large curve, goes over this. And the idea is, and then, whoop, the one that's pointing directly away, though, goes away forever. This one kind of curves over. And the idea here is when we draw positive charges, the charges come out from it. The arrows originate from the charge and then go out. But for a negative charge, the arrows come in. I like to think of this as kind of like a bathroom sink, where the source of water, the positive, is the faucet, and the sink or drain is where the water goes, or the electric field lines go into. It's just a mnemonic. It's a bathroom sink is not actually electric field lines. But then, I guess, moving on to the topic of reality in general, you might be thinking, well, do electric field lines really exist? You guys have been, these are being drawn, and they're talked about as if they're real things. And I guess the real answer for that would be no one really knows. Science isn't so much about what reality is about predicting and controlling reality and modeling. So if your crazy model using rainbows and unicorns and bunnies perfectly predicts the physical world, then no one's going to care if we actually have bunnies, unicorns, and rainbows that are driving the physical realm. As long as your model predicts what's actually happening, that's all science is really going to care about. So the idea of, well, does a positive particle really put out these electric field lines, and do these electric field lines then interact and get sucked up by the negative charge, causing force between the two? Maybe, probably not. I don't know. No one knows. But it's really kind of an irrelevant question, because this model really works pretty well for describing physical phenomena in life. So try not to get too hung up with the idea of, is this real, is this not real? And you really can't go too deep into a lot of the questions. Like, when you're a kid and you ask your parents, they tell you, you can't go on that ride, you're not tall enough. And you're like, why? And then they give you an answer like, well, I was short at your age, you're short at this age, and you're just too short to go on that ride, kiddo. And they're like, why? And they're like, well, maybe the safety bar, and you can go like 5 or 6 times, and the parents are like, I don't know, that's just what God says. I don't, give me a break here. When you're talking about electromagnetism, often you can only ask why maybe once or twice, and then it's like, well, that's kind of the state of the art of science here. We really don't know the answer beyond that. And so there's the amount of, we have a lot of data, we know a lot of the way things work, but the reasoning behind why a lot of that works is a very thin veneer in electromagnetism. So it's not that we don't know a lot, it's just that we have a very thin level of knowledge over many things, and then you can't go too deep, can't go too profound in that body of knowledge, that lake of knowledge, if you will. All right, so that's kind of an idea of how you can draw electric field lines. Let me give you an alternate way of drawing them real quick. They usually aren't, almost never drawn this way, but it's not actually a bad way of drawing them. So, well, it's at least acceptable. So here we drew electric field lines where the electric field is very strong, close to the charge, and it gets weaker as you go. Another way you could draw that would be concentric circles. So let's make this one, I don't know, blue, Yeah, that's good. Make, maybe if I start big and then go small, I'm good with that. Right. Bring to front. Aha, aha. Bring forward. There we go. Or I can just change it so that there's not. There we go. Change the opacity. That's what I was really going for. Make big. Darn you, opacity. Aha, at least that one's opacity. Alright. So now I got this crazy setup of concentric, semi-concentric, slightly off-centered circles. So you could say that, let's do purple. So you could say that this here is your charge. And then you could say that each of these lines here, electric fields are generally measured in newtons per coulomb. So you could say here that this might be like the, 10 newtons per coulomb. This would be 9 newtons per coulomb. This would be 8 newtons per coulomb. And then this would be the actual charge itself. And before we drew the lines as arrows, as a vector field, where these would be not equal potential, because that's for voltage, which you do see this line voltage, which we'll talk about later. You can say that these are equal strength electric field lines. So this line here would show you where you have a constant strength of the electric field. And then the vectors for the electric field would be perpendicular to it. You could think of this kind of like as a topographical map. Like you see like one of those topographical maps where you see the hill and the concentric, semi-funny looking oval shaped things, and then it shows you the elevation. And when you see a bunch of the lines close to each other, you know that that'd be a very steep area. That's another way of representing the same concept here of electric fields, where you draw lines not showing the direction of the electric field, but you draw lines that are perpendicular to the electric field, and it's at a constant field strength. So we're not going to deal with that much, but it's good to understand that that exists, and that it's just another way of representing the concept here. All right, so then the real value we have with electric fields is being able to put a bunch of charges together in complex shapes to get something that's we're able to create a simple electric field from a complex series of charges. That sounded more complicated than I meant it to be. Copy, paste. I'll put this guy over here so I don't lose him. So let's take a quick example. We'll do, a few. 4. Is 4 a few? I don't know anymore. All right. There we go. I'm good with that. Do they look equally spaced? Sort of equally spaced. Semi-equally spaced. All right, so we have 4 charges. These are positive because the field lines go out. And then what we're concerned now with is the electric field. So I'm going to take this and ungroup this object. Can I do that? Ungroup objects. Interesting. So what we're going to be concerned with is the electric fields, specifically on this side first. So each of these electric field lines kind of represents a portion of the vectors. So I can really just take the lines from each of these and separate them out as individual vectors. And then add them together. This is not a formal proof. This is just a make you feel okay, warm and fuzzy proof, which for the AP exam is probably good enough. You only need, it's mostly multiple choice. Well, there are some free response. About half the test is free response. And those are darn tough. But there are some multiple choice, and you only need about 60%. You could probably pass the test with 50%. So, okay. So here are the vectors. So the idea here then is these are all the vectors going towards the right. Everything else isn't. The left side is symmetrical to this, so we're good. You can kind of sort of see where the ups and downs from the middle would cancel. And so if we look at this, Boom, boom, boom. That's close enough. And we'll do red. If you add these vectors together, you can see here they decompose this vector like this vector like that, and then you decompose the second vector in a very similar manner. This vector and that vector, the two vertical ones, are going to cancel, and you have a resultant vector towards the right. And you can see that will happen with all the up and down vectors. And there's 1, 2, 3 up, 1, 2, 3 down. And they'll each cancel each other and give you a composite vector to the right. And vectors that are straight to the right, well, they're straight to the right. And even though this example came out perfectly to represent as such, this is just an approximation. An approximation that gets better the thinner and more dense the charges are within the object plate. So we have all these charges within this plate. What it's going to do is going to create an electric field that is uniform away from it. Yep, it'll create a uniform electric field. Now, this is, again, just an approximation, but you'll hear about parallel plate capacitors, and the whole idea between a parallel plate capacitor is you got a set of positive charges, you have a set of negative charges, and they create a uniform. And this uniform electric field is kind of an example of how we have a relatively complex conglomeration of charges, which creates a very simple electric field. And that simple electric field is what adds value to the F equals EQ equation. Now, one quick side note, as I've mentioned earlier, and I'll probably mention it a million times more, the equation that I actually use when I'm doing problems involving charged particles and electric fields is F equals EQ vector vector plus QV cross B. But for the most part here, we're going to have no magnetic field, so that just goes to 0. Another useful collection of charges is a sphere with a whole bunch of charges. I probably should draw it bigger. Doesn't matter. Holds for small and large. So the idea is if you have a sphere, you can approximate the sphere as a point charge for another charge Q over here. So this section, look at the middle, combine all the charges into one super small point charge, and you can approximate that as such as well. And that is pretty much all the information we need for electric fields. So, move on to a couple problems. Given a uniform, Given a uniform electric field in the positive x direction, check, a small sphere, check, with mass 0.025, okay, and a charge of 3 microcoulombs forms a 10-degree angle with a vertical. Find the magnitude of the electric field. Okay, so first we start by drawing a picture, mostly drawn for us. We'll get blue, because everyone loves blue. And we'll draw gravity, mass times gravity, and it says a electric field to the right. So electric field goes this way, and so we have the equation force equals EQ plus QV cross B. So we know that the magnetic field is 0, so this part goes to 0. This is supposed to be a vector, that's supposed to be a vector, and so for a positive charge, because positive's positive, it's going to be in the same direction as the electric field. So the force, which will be E times Q, is in this direction. Maybe make a little vector on gravity there too. All right, and it makes sense then since it's being pulled this direction. So whenever I see a uniform electric field, first thing that I should have done, which I didn't, but I should have, was I draw parallel plate capacitors. And this is just as a reminder of what's going on here. So for a parallel plate capacitor, we'll have a bunch of positive charges over here, negative charges over here, and this will give us an electric field from the positive to the negative. And this is a good way of visually keeping track of how the electric field is going on. So if we look at this point charge Q, well, ball Q, it makes sense that since it's positively charged, because they gave us positive 3 microcoulombs, make it a positive, go with the red, positive. It makes sense that it's going to be pulled towards the negative plate and pushed away from the positive plate. Opposites attract, like charges repel. And so when they say we have an electric field in the positive X direction, this direction, we can then draw the 2 parallel plate capacitors with the convention that the electric field starts from the positive and terminates at the negative. And so drawing the parallel plate capacitors kind of helps keep the whole concept in check. All right, so now we're trying to find the value of the electric field. Okay, so we're just going to start writing up everything we know. So for gravity, remember from, so let's see, we probably got tension up this direction. So I'll draw a tension triangle. So this will be tension, this will be tension in the y direction, this will be tension in the x direction. These are just the decomposed vectors. Actually, I guess it would be the other direction of the tension. So we know that the vertical, and these all have to equal out because we're going to assume that it's not moving here and that they gave us a reasonable problem. So we know that the tension up in the y direction is going to be canceled out by the mass times gravity in the down direction. So tension in the y direction, which is, see, this is theta, cosine of theta equals cosine theta times tension of that direction equals mass times gravity. Is that true? Cosine theta. Yep. And we know that that theta is 10 degrees up that direction. Tension, cosine. Yep, I'm good with that. All right, and then we're going to do the same thing for the x direction. Tension in the x direction equals sine of theta, which is 10 degrees, times tension equals, and this time we're going to have electric field times Q, where the only thing we don't know here is the electric field. Okay? So let's see, we could solve both sides for, yep. All right, so if we solve both sides for tension and set them equal to each other, we'll get mass times gravity over cosine of theta equals electric field times Q over sine theta. So what we did there is we just solved for the tension by moving these guys over, that over there, and then set them equal to each other. So we know mass, we know gravity, we know theta, and we know the charge. So solving for Q, or E, we have electric field equals sine of, what was theta? Was it 10 degrees? 15. 10 degrees. Sine of 10 degrees over cosine of 10 degrees times mass times gravity over Q. All right? And then working this out. So sine of 10 is about 1/6. Cosine of 10 is about 1. I am really being fairly generous on my estimations here. Mass is 25 times 10 to the negative third, because it's 0.025, is that right? 1, 2, 3, yep, and it's measured in kilograms. Gravity is about 10, and that's meters per second squared. And then Q, is it 3 or 6? 3. 3 times 10 to the negative 6 coulombs. All right, so cancel, cancel. We have 10 to the negative 3. Let's see. So this is the same as 10 to the third up here. This becomes 10 to the fourth. So this becomes 25 times 10 to the fourth. 25 times 10 to the fourth over 6, which is about 4 times 10 to the fourth. Seems like a lot. Yeah, that's how to do it. Okay, so it looks like we have the electric field then equals 4,000 newtons per coulomb. That's a pretty strong, stout electric field. Yep. Okay, and that is how we would do the pendulum problem. So we got a pendulum, we have mass and electric field acting in opposite directions. We get the sine and cosine of theta, and then we set things equal to each other. And since there's no acceleration, total force equals 0, and you solve. Make sense? Excellent. So we have another problem. The electrons in a particle beam, okay, so it's going to be electrons that are moving, have a kinetic energy. Energy kinetic is 1.6 times 10 to the negative 19th joules. What is the magnitude of the electric field that will stop these electrons at a distance of 1 meter? Okay, so the way this works is we have ourselves an electron, so E minus. It goes this direction, and there is an electric field that makes it stop. So the way I'm going to determine which the magnetic field is just by reasoning it out. So if we have a parallel plate of positive charges over here and a parallel plate of negative charges over here, the electron will eventually slow down and then change directions. And it's asking us the magnitude of the electric field. I'm going to assume a uniform electric field here that will cause these electrons to stop. And it's telling us that this distance right here is 1 meter. And talking about kinetic energy, so we're looking at work. And so start by writing up equations. So first we write out the equation for work. The mnemonic I use is that work makes me mad. It doesn't actually make me mad. Work is good for the soul, but it's a good mnemonic. And so to get a little bit more realistic, we have F force times distance. And to get a little bit even better, work is the integral of F dot dr, where the dot product is the cosine of the angle between the force and the motion. So in this case then, so we're going to assume that the electric field is parallel in the same direction as the motion. And so for this, we know that, let's see here, this would be E, electric field times Q dot dr. So we have the equation force equals EQ plus QV cross B. We have no magnetic field, so this is 0. So this side is 0. We're left with electric field times Q is the force. And since these are constant, we can pull them out of the integral. Work equals E times Q. I'm going to leave off the vector at that point because the dot product of two vectors gives you a scalar, and work is a scalar, which is kind of what we're looking for here. So we know that the total distance is from 0 to 1. We'll call this 0 meters. We'll call this 1 meter. So this right here goes to 1. Electric field, that is unknown. Work we're given is 1.6 times 10 to the negative 19th joules. And then Q is given us as the charge of an electron. So to figure this out, we rearrange for electric field. So electric field equals work, which is just energy measured in joules, over Q times 1, which equals 1.6 times 10 to the negative 19 over charge of an electron. Go to Wikipedia, clickety-clack. Electron. Alright, so let's see what we got here. Electric charge, 1.6 times 10 to the negative 19 coulombs. Not a coincidence. 1.6 times 10 to the negative 19th coulombs. This is joules. Electric field is measured in newtons per coulomb. And so this 1 here probably is actually meters. So then I'm going to assume everything cancels out. This gives us 1. So electric field would be electric field equals 1 Newton per coulomb. So here, electrons in a particle beam have a certain amount of energy, and then we are able to change that kinetic energy into potential energy using an electric field, and it gave us a specific distance with which to do that. And then we just drew up the pictures. Electric field means draw parallel plate capacitors to kind of get the visuals correct. And then write up the equation for work. We knew an equation for force, so we plugged that in. Things were constant, so we pulled them out of the integral, making the integral very simple. Okay? Aha! An AP question. A proton moving along the positive x-axis. Okay? So, x, proton, moving along the positive x-axis, I assume it's moving in the positive direction, enters an electric field that is directed along the positive y-axis. So an electric field here. What is the direction of the electric force acting on the proton after it enters the electric field? So this is F equals QE. Sometimes I write EQ, doesn't matter. QV cross B. Alright, so we know that there is no magnetic field, and so this says that the force is going to be the same as the electric field, assuming we have a positive charge. And we do have a positive charge because it's a proton. So what is the direction of the electric force going to be? It's going to be along the positive y-axis, because that's the direction of the electric force is in the positive y-axis, so they'll be the same. Pretty simple, pretty straightforward, not that bad. Actually, it wasn't too bad. And you get about a minute to do these problems. So you could probably pick up a few extra seconds. If you can solve this in 45 seconds, go for it. But it feels like there could be lots of tricks here. Because like if you had an electron instead of a proton, then you would get a negative here, and then you get the opposite direction. Or if you had the magnetic field, which we haven't talked about yet, then you have to do the velocity cross B, which would be a cross product, which you can do, but at this point it's easier not to. Okay, moving on. Free response question. This is a big question. You usually get about 15 minutes or so to solve these problems. So they are possible, but gee willikers, look at all these parts. This is a serious test. Serious test. Alright, well, okay. The square of a side, A, check. Above contains a positive charge plus Q, check, fixed to the lower left corner, and negative point negative Q, check, at the other three corners of the square. Point P is located at the center of the square. Seems reasonable. On the diagram, indicate with an arrow the direction of the net electric field at P. Okay, so we discussed with electric fields, they are radially outwards. So for positive Q, they're all going to point inwards. And for the negative Q's, they're going to point, or positive Q, they're going to point outwards, negative Q's, they're going to point inwards. And then, so for this, we're going to extend this one, we'll go towards there. This Q would go there. This Q, if we extended that arrow, would go that way. And then we'll extend this Q, the negative Q would go towards the negative Q. So the two Q's, top left corner, bottom right corner, cancel out. And the bottom left corner, top right corner actually reinforce each other. And so the net arrow would be this direction. The net electric field. Yep. So what we drew was all the electric fields, and then when we add them together, that would be the net. Draw the equations for each of the following in terms of the given quantities and fundamental constants. The magnetic magnitude of the electric field at point P, the electric potential. We haven't talked about electric potential yet, so we'll get to that one later in another video. The magnitude of electric field. Okay, so we know the electric field from Coulomb's law. So F equals K Q1 Q2 over R squared. So we know that negative Q's on both sides are going to cancel because they're symmetrical. And plus Q and negative Q are just going to have the opposite signs. So the electric field would be K, I was going to write Q2 over R squared. So for positive Q, we'll have E positive Q equals K Q positive Q over R squared. And then for the negative Q, we'll have K negative Q over R squared. And then we know that those are going to act in the same direction because we already just looked at it up here. So what we're going to have then is E net, electric field net, equals K 2Q? Yep. 2Q over R squared. Because we add these together. Now you might think that, oh, we have a positive Q here, negative Q here. And that's true. So you could be like, okay, they're acting opposite each other, but they're on opposite sides of P, so you kind of get this double negative situation. It's better off not thinking of it algebraically and just looking at the picture and be like, okay, these are going to be acting in the same direction. So focus more on the picture and less on the algebra, because algebra just tends to be prone to error. And if you can skip to the answer that you know is correct, that's generally better in life. All right, so then R in this case, though, we need to find out what R is. So we have A over 2, A over 2. What I'm doing is taking these sides right here and just looking at the length to try and find the radius R, which is the middle. And that would be A over 2 squared plus A over 2 squared square rooted, which is purple. So we're going to have A squared over 4 times 2 square rooted. So this will cancel and give us 2, which then equals a over square root of 2. You're not really supposed to have square roots in the bottom, I guess. So this would be square root of 2 times a over 2. You just multiply the top and bottom by square root of 2. Okay, so then our total electric field net would equal, at point P, K times 2 times Q all over probably shouldn't have taken the square root. So this squared. I'm going to go back to this one and do this one squared. So we'd have a squared over 2 multiplying by the reciprocal. So we'd have 4kq over a squared. Yep, that makes sense. 4kq. And when an electric field had a good dummy check, just make sure that there's only one charge up top. For force, you want to have 2 q's, q times q. You want to have 2 q's multiplied by each other, so q times q, and for electric fields, you want to have 1 q in the top and generally a squared component in the bottom. So that is our answer for BI. A positive charge is placed at point P. It is then moved from point P to point R, okay, so directly down, which is the midpoint of the bottom side of the square, which is the bottom side of the square. As the charge is moved, is the work done on it by the electric field positive, negative, or 0? Okay, so work done by electric field. So we've already determined that the electric field is in, so this is point P, the electric field is in that direction. So the force is going to be up and to the right, and it's a positive charge. So we know that the force will be in the same direction as the electric field, as we discussed earlier. And what we're doing is we're taking the charge and moving it down here. So work equals F dot dr, integral, line. And so the dot product is the cosine of the theta between the two angles. So you can think of it as theta in this direction, or you can think of the dot product as the projection of one vector onto the other. So this is actually a time when another color would be useful, as opposed to all the other times when I just do it for my own amusement. So if we're projecting this motion, which is the r, onto the f vector, we're going to get this, which would be f dot r. I know I should be using dr, but it's easier and more convenient to do it this way. So we're projecting the displacement onto the force vector, and so that's an alternative definition of the dot product, which is really useful. And so we can see that f dot r is in the opposite direction of f, and so the work equals f dot dr would be negative. So if the charge is moved, the work would be negative, because it's the another way of thinking of that is the displacement is in the opposite. It's not actually exactly opposite, but contrary to, not in the same direction as the force. So displacement is in the opposite direction of force. Describe one way to replace a single charge in this configuration that would make the electric field at the center of the square equal to 0. And the next one talks about electric potential, so let's ignore the second one. Okay, so which charge could we replace to make the electric field 0? Well, we already had the top left and bottom right corner cancel each other out, so we're good with those. But what we might want to do is have the bottom left and top right cancel each other out. So one way we could do that is we could replace this with a negative charge here, or we could replace the top right with a positive charge. Either way, what would happen is it would flip one of the vectors associated with the electric field so that they would cancel out the other one. So we move it. So we make this, let's go with green. Make this guy negative. The charge now points inward. We then get, or the electric field now points inward, get a vector pointing towards the bottom left, and then they all cancel out. So this would be, and I'm not going to use proper English. You should use proper English. So bottom left to negative. You should probably actually write out complete sentences. Okay, and that's what we have for the electric field. So important takeaways. Electric field is a vector field, which basically represents the gray, which more or less represents kq2 over r squared, and we use the electric field as a way of calculating the force. Electric field is convenient because it allows us to take a whole bunch of different points, put them together, and then ignore the fact that they are separate points and look at just the field that's created by those points. All right, next time we'll talk about insulators and conductors. Thank you much. Take care.